Welcome to this presentation. This session demonstrates a practical application of dynamic programming to solve a crucial resource allocation problem in the context of global health. Specifically, the challenge involves optimally allocating a limited number of medical teams to 3 different countries, with the objective of maximizing the total improvement in life expectancy. This case study is designed for undergraduate and graduate students who seek to deepen their understanding of dynamic programming's utility in solving complex, real-world optimization challenges. We invite you to explore this powerful methodology with us as we solve this problem step by step. Let's now define the problem we aim to solve. The World Health Organization plans to send 5 medical teams to 3 different countries. Our objective is to determine how many teams should be allocated to each country to maximize the total increase in life expectancy across all 3 nations. To make this decision, we are provided with the data in this table. Let's break down its structure. The rows, numbered from 0 to 5, represent the number of medical teams that can be assigned to any single country. The columns, labeled 1, 2, and 3, correspond to each of the 3 different countries. Each cell within the table shows the resulting increase in life expectancy, measured in people years, for a given allocation. For example, let's look at this specific cell. At the intersection of the row for 2 medical teams and the column for country 1, we see the value 70. This means that if we allocate exactly 2 medical teams to country 1, the life expectancy in that country is projected to increase by 70 people years. Similarly, sending 4 teams to country 2 would result in an increase of 110. Our core challenge, therefore, is to find the combination of allocations to countries 1, 2, and 3 that sums to 5 teams and yields the highest possible total increase. We will now proceed to solve this problem by defining the key elements of dynamic programming in the context of our medical team allocation. Stage, denoted by N. In our problem, each country represents a distinct stage. Therefore, we have 3 stages corresponding to the 3 countries. State variable, denoted by I. The state represents the number of teams that are available for allocation at the beginning of each stage. Decision variable, denoted by K. The decision variable is the number of medical teams we choose to allocate to the country at the current stage. Transition function. This function describes how our state changes based on our decision. The formula J equals I minus K defines this transition perfectly. The number of teams available for the next stage, J, is simply the number we started with, I, minus the number we just allocated, K. And most importantly, the return function. This is the core of our optimization. The function f sub n of I calculates the maximum possible increase in life expectancy we can achieve from the current stage all the way to the end, given that we have I teams available. To find this maximum, we evaluate the expression for all valid decisions for k. This expression consists of 2 fundamental parts. The first component is the immediate return. The direct increase in life expectancy from allocating k teams in the current stage, n. We obtain this value directly from the data table provided. The second component is the optimal return from the previous stages. This is simply the optimal value taken from the previous table we solved. In essence, at each stage, we sum the immediate gain with the optimal gain from all future decisions, and then select the allocation, k, that maximizes this total sum. We will now commence the solution process using the backward recursive method. Our analysis begins at the final stage of the problem, designated as n equals 1, which corresponds to country 1. It should be noted that this initial stage is fundamentally straightforward. As this is the terminal stage, there are no subsequent stages to consider, and therefore, the optimal future return component is 0. The objective simplifies to maximizing the immediate return from the allocation to country 1. We will now populate the solution table for stage 1. The column I denotes the state variable, representing the number of teams available, ranging from 0 to 5. For each state I, we must determine the optimal allocation, k star sub 1, and the corresponding maximum return, f star sub 1 of I. Let us proceed row by row. For the state I equals 0, we have 0 teams available. The only possible decision is k equals 0, which yields a return of 0 from the main data table. Thus, we record k star as 0 and f star as 0. For the state I equals 1, we have 1 team. Our decision k can be 0 or 1. Referencing the data table for country 1, an allocation of 0 teams gives a return of 0, while an allocation of 1 team gives a return of 45. The maximum is 45. Therefore, the optimal decision k star is 1, and the optimal return f star is 45. For the state I equals 2, with 2 teams available, k can be 0, 1, or 2. The respective returns are 0, 45, and 70. The maximum return is 70, achieved when k equals 2. Consequently, we set k star to 2 and f star to 70. For the state I equals 3, the possible allocations for k are 0, 1, 2, or 3, with returns of 0, 45, 70, and 90. The maximum value is 90, corresponding to an allocation of 3 teams. We record k star as 3 and f star as 90. For the state I equals 4, following the same procedure, we compare the returns for allocating 0, 1, 2, 3, or 4 teams. The maximum return is 105, which results from allocating all 4 teams. Thus, k star is 4, and f star is 105. For the state I equals 5, finally, with 5 teams available, the optimal strategy is to allocate all 5, yielding the maximum possible return of 120. We therefore set k star to 5 and f star to 120. As is evident from this analysis, for country 1, the return function is monotonically increasing. This leads to a simple conclusion for stage 1, the optimal decision, k star, is always to allocate all available teams, making k star equal to I. The final column, f star sub 1 of I, is therefore a direct copy of the values from the country 1 column in the main data table. This concludes the calculations for stage 1. Having completed the calculations for stage 1, we now move backward to stage 2, which corresponds to country 2. In this stage, for each state I and each decision k, we consider the immediate return from country 2, plus the optimal return from the previous stage. Let's populate the solution table for stage 2. For the state where I is 0, with 0 teams, the decision is k equals 0. The return is 0, plus the future optimal return of 0. The total is 0. Thus, f star 2 is 0. For the state where I is 1, we consider k equals 0 or k equals 1. If k is 0, the return is 0 plus 45, which is 45. If k is 1, the return is 20 plus 0, which is 20. The maximum is 45. So, the optimal decision is 0. For the state where I is 2, we evaluate k equals 0, 1, or 2. For k equals 0, the total is 70. For k equals 1, the total is 65. For k equals 2, the total is 45. The maximum is 70, achieved when k is 0. For the state where I is 3, the decision k equals 0 gives a result of 90. The decision k equals 1 also gives 90. And the decision k equals 2 also results in 90. The decision k equals 3 gives 75. The maximum value is 90. Since the decisions 0, 1, and 2 all result in this maximum value, we list these as optimal decisions. For the state where I is 4, comparing returns, the maximum is 120, occurring when we allocate 3 teams. So, the optimal decision is 3. For the state where I is 5, with 5 teams, the maximum return is 155, which is achieved when we allocate 4 teams. This completes the calculations for stage 2. We have now reached the final stage of our dynamic programming process, stage 3, for country 3. Here, we must determine the best allocation of our 5 medical teams. To do this, we will evaluate each possible decision for country 3. Let's walk through the calculations for our 5 teams. First, consider allocating 0 teams to country 3. This gives an immediate return of 0, plus the future optimal return of 155, for a total of 155. Next, allocating 1 team gives an immediate return of 50. We add the future return of 120, resulting in a total of 170. For an allocation of 2 teams, the sum is 70 plus 90, which gives us 160. If we allocate 3 teams to country 3, the return is 80 plus 70, which equals 150. With 4 teams, the return drops to 145. And finally, allocating all 5 teams to country 3 gives a total return of 130. By comparing these outcomes, we see the maximum return is 170. This is achieved when we allocate 1 team to country 3. This is our optimal decision. Now, we trace back to find the full optimal policy. Since we assigned 1 team to country 3, we have 4 teams remaining. Checking our stage 2 results, the optimal decision for 4 teams was to allocate 3 teams to country 2. This leaves us with 1 team for country 1. Therefore, the final optimal strategy is 1 team for country 3, 3 teams for country 2, and 1 team for country 1. This distribution maximizes the total increase in life expectancy. Thank you for watching this presentation. If you found this tutorial on dynamic programming helpful, we invite you to explore our YouTube channel, Growing Science, for more educational content.